this text comments.
I'm going to introduce our first speaker for the high energy seminar. This is Ari. She's visiting us from Purdue University. Ari was previously a graduate student at Northwestern University working with Kiki Calagera, and she's going to be telling us today about some of the work that she did while she was a graduate student. Tomorrow, if you're inclined, she'll also be presenting at the ITC luncheon, where she'll be talking about a new project related to LSST data. So, thank you.
Thanks, Dan. So, never been to Harvard in this capacity. I actually did a summer internship with the Smithsonian Astrophysical Observatory, and believe it or not, I thought that was the extent of the astronomy department. I used to walk by here and I used to see the domes, and I was like, nah, this is where they do the observing. So, but I walked in for the first time, when I visited, and I was like, okay, I think that's where the real stuff gets done. But anyway, really excited to be here. Thanks, Dan, for the invitation. So I'm going to talk to you about, as Dan mentioned, my thesis work. So for the very few people out here who want an introduction on what type 2b supernovae are, so they are the class of supernovae that are thought to explode with a tiny amount of hydrogen on their surface. The ensuing supernova has the characteristic that the spectral features early in their evolution evolve such that when you initially exhibit hydrogen lines, and those disappear later as the evolution proceeds. Just like other strict envelope supernovae, let me step back. Type 2b supernovae are classed within the strict envelope supernovae branch. And they are interesting of all the strict envelope supernovae because as a group they are quite abundant. So, like depending on how you which statistic you believe, about 10 to 12% of all core collapse supernovae are type 2b supernovae, and a significant fraction, probably about a third, of the strict envelope supernovae are type 2b supernovae. They're further interesting within the class of strict envelope supernovae because we have 5 candidate progenitors. It's difficult to verify this, as my boss will keep reminding me that these are all extragalactic, and you look at Cassia, which is the only galactic supernova remnant associated with type 2b, and there is no companion. Like for instance, like these candidate progenitors, any identification of any star in that field is hard. So any attribution to a pre-explosion image that shows the source there has to be interpreted with caution. There are 3 with evidence for a binary companion, and I call this evidence because they're from varying lines. None of them have shown confirmed identification of the SED from the companion star left over behind. So I'm going to stop right there. But it's interesting because they have multiple other pieces of clues that can allow you to constrain the progenitors. So as with any strict envelope supernova, the question from the theorist side is, how do you explain the stripping process? What could cause the stripping? And people typically point to multiple lines of evidence here. So, for instance, people invoke stellar winds, stellar rotations, stellar eruptions, and binary interactions. And while I will not talk about the stellar rotation and stellar eruptions in this talk, there is no reason to exclude them a priori. There is a lot of good motivation to think about binary interactions as the processes that lead to the stripping of the progenitor star, due to indirect evidence that has nothing to do with stellar evolution modeling. So, for instance, you can just count up the percentage of stars that are in binaries, and you expect that many of them are going to interact in some binary fashion somewhere in their lifetime. You expect that actually winds that these massive stars exhibit are typically clumped. So if they are clumped, that means that you're overestimating the wind mass loss rate. That takes away some of the blame from the stellar winds, because then if stellar winds are weak, then how do you cause the stripping? Given the fact that we know that winds are actually weaker than we typically use in stellar evolution modeling. There is a high fraction of stripped envelope supernova progenitors that you cannot explain just by a single star evolution modeling. I love this paper by Nathan Smith. It's sort of like very approaches this question of whether, how far can we go with just playing with the initial mass distributions and stuff, and see at what point, without doing any evolution modeling, can you explain some of the rates that we see for strip tunnel of supernovae. And there are others, and I don't want to get into them because I don't want to get into my science. So I was interested in the question of what dominates the stripping in type 2D supernovae. And I wanted to make sure that I did the following. That first, I need to make sure that I explain whatever modeling I do, I explain all observations that we have for strip tunnel supernovae, for type 2B supernovae, that includes for type 2B supernovae, these types of stuff that we will talk about later. Make sure that we do this statistically. So like we take into account the fact that any progenitor that we see has an a priori likelihood of being born that way. So like make sure we take that into account and just sort of not look at a certain progenitor and explain that, see that it explains the photometry. It's like also asks whether that's likely to happen in nature. And make sure that in the end you need to have testable predictions for your models. So like if I see some properties that are implied by my modeling, make sure that eventually those can be verified in the future, and if they don't, then that means that my models are no good. So for instance, what we did with this was we modeled a huge parameter space. This is all the thesis work. So we had a huge grid that we ended up having like 150,000 models. Not all of these are type 2Bs, but the coverage consisted of that many models that we dealt with eventually. And we selected out in that parameter space. So let me actually have the time right today in this talk to point out that we had two metallicities that we covered. We had solar and we had subsolar metallicity. We had singles and binary stars. If you stare at this a little bit, all the experts in the audience will see that this is quite comprehensive. And I'll show you the parameter space in a little bit to give you a sense that this is quite big. Like I said, I don't consider rotation, so all of these stars were non-rotating. We did vary mass transfer efficiency, and I'll talk about that as well. As such, I think this is the portion that's most important. That in the models that I use, this combination of set of wind perspectives. These are not set in stone. As I mentioned in my earlier slide, that winds are expected to be clumped, and these are what we have been using so far. But if you look at current work that tries to better constrain the winds, some of this is expected to be overestimated by a factor of 2 to 3, depending on how you make that estimate. And but 2 to 3 may not seem like much, but if you actually take that amount and you add it over the evolution lifetime, it matters significantly. What I want you to take away from this is that even though I have used this, there is nothing that says this is sacred and cannot be changed. And in fact, I'm going to ask whether I can change this. So keep that in mind. So when I model these from birth all the way up to very close to core collapse, I just select progenitors that explode with a tiny amount of hydrogen. So there is no attribution that all of these will end up as type 2B, but because we don't have, since I don't model the light curves or look at the spectra, which is hard, so look at Luke Desart's work, who's like extensively trying to see whether a progenitor structure produces a type 2B like evolution in spectrum. It's hard to do. But most people use something like this as a first order approximation to look at type 2B progenitors, which is what I do. So first let me just show you the parameter space. So for singles, so again, like I said, I look at two different metallicities. At solar metallicity, I have a narrow range that is dictated primarily by my mass loss prescription. So this is entirely set by the fact that the mass loss should be just enough that for that mass range you end up with that particular amount of hydrogen left over. So that's very set, and it's a function of the mass loss rate I used in my models. At subsolar metallicity, obviously, because we have metallicity dependent winds, there is very weak winds. And if you look at more recent work by Tugul-Dursuk, Boll et al., you'll find that there is, even from models, we now expect that some of the stars as massive as these will not experience explosions. So we don't count these at all. So we just say that these are going to implode quietly, won't have successful supernova explosions. Within the binary space, I'm just showing here two mass transfer efficiencies because it's easy to directly compare them. So assume these are one-to-one analogs. At solar metallicity, if you just sort of imagine this as sort of cuts through your parameter space, and then you compare that with subsolar metallicity, you can just see that there's way more colored area. And the reason for that is you end up having way many more progenitors possible at low metallicity. And this is again a function of winds. So in binaries and in mass transfer, you will in most of these cases end up experiencing mass transfer to a certain extent, and you always have a certain amount of hydrogen left over, which is good for 2Bs, unless you have so much time remaining in your lifetime that you have strong winds, and then you can lose all that mass. So you won't end up exploding with hydrogen. You will end up having some amount of you will end up being completely stripped and not a type 2B progenitor. So for most of these cases, the reason why this red stuff exists at subsolar metallicity but not at solar metallicity is because that after mass transfer you just have such weak winds that you fail to completely strip the stars, which makes them type 2B progenitors. So what we did was we went ahead and we computed rates. So what we did was we varied all sorts of things that we don't know for sure. For instance, we don't know the priors very well for the IMF or the initial mass distribution for the orbital period, or exactly the definition of what makes what is a type 2B supernova progenitor based on its envelope. So we vary all the things that we don't know, and we come up with a conservative range from our calculations for what the theoretical predictions are for the rates. And what I show you here is the observational side of things. And what I want you to see is that if you look at high metallicity, so by the way, this number at low metallicity is dictated by small scale statistics. So, you know, we take this with huge amount of salt. Like, we don't know this very well, but if you just look at this one and then you look at the high metallicity predictions, so this is singles and binary. So if you take all the population together, at best, even if you're very, very optimistic, at best we can produce forget about the decimal points, whatever. If you compare this number to that one, we disagree within 2 sigma. So our models are not able to explain the rates from observations. However, this doesn't happen at low metallicity. Now, I told you to take this number with a grain of salt, but still, in many cases within the 2 sigma, obviously the 2 sigma is hard to take here, but whatever, it's consistent. But what I want you to think about is the following. This thing that I said earlier, that the reason why low metallicity progenitors survive is because they have the winds that allow the star to retain the hydrogen envelope that it has when it finished mass transfer. But I also told you earlier that actually at solar metallicity you also expect that the winds will be weak. So if you were willing to modify the physics, if you were willing to ask that if I had run, so let me go back to the slide here. If I had run any of my solar metallicity models with weaker winds, would I have not populated some of this? Now I haven't run these models, of course, and there is work that has been done to see whether you can reproduce some of these calculations with weaker winds at solar metallicity. But Sun Chul, for instance, did some very nice calculations to show that actually you start populating this part. So if you take the caveat that my models within reason can be modified, and I can then use perhaps these rates as a proxy for what is observationally possible. So these are obviously like weak winds, if you will. Then the consistency becomes better. So the thing that we, at the end of this paper, we concluded was, now of course, we wanted to ask what the progenitors of type 2B supernova are, and the answer is it looks like it could be binaries. But the thing that you have to take away is that not all the physics that we have here is correct. So you have to consider that binaries are likely progenitors of type 2B supernovae, with the caveat that if you want to explain the rates, you need to dial down the winds that you have in the models. Okay, but all of this is theory, and you guys are mostly observers. I think the word. So let's look at the second part of the paper, where I was interested in looking at observational implications. So what I did for my thesis was I wanted to do this statistically. I had a huge bit of models, so I wanted to make a statistical comparison to all observations. So I went and compiled sort of all the various literature constraints that we had for properties of the progenitors that we've derived by various means. So you can look at light curves, and you can do light curve modeling, and you can get these numbers. You can look at the pre-explosion images and constrain some progenitor structure properties. It's its luminosity or effective temperature, and from X-ray and radio observations. And actually this is interesting for you guys here, because for much more of the instances for these type 2Bs, we had constraints from X-rays and radios for their circumstellar medium properties. So given that I have a large grid of models, and I think that for instance the low metallicity models are more likely to be representative of what's going on. Let's try to compare. Keep in mind that I will start more focusing on the low metallicity model side of things. And the reason for that is, there is, in all cases, and I will go forward, solar and subsolar metallicity models aren't very distinguishing. They don't have so much of a distinguishing power to, like, if I take both the set of models and I try to explain the observations, many times within the margin of error, we're always able to explain the observations. So the thing that narrows the focus down is the rates. The fact that, so even though solar metallicity models can explain many of the observations, it's just that since they don't produce the rates, we try to focus on the solar metallicity model side of things. So anyway, let's go step by step and do this type of analysis. So like for instance, so this is an example, as I mentioned here. So this is the solar metallicity models. This is low metallicity. The low metallicity models are favored for rates. But anyway, so here, I guess focus on this plot. So this is, for instance, the hydrogen envelope mass that we expect from the modeling, the helium core mass, and the radius. And all the grayed regions are what we expect, the observationally derived values from the previous table that I was showing. So as I was mentioning that, most of the time that, we are able to account, the observations are on top of the models for many of the cases. This particular plot is not very enlightening, so I will not spend too much time on it, except the fact that, for instance, single stars here, this is known very well by the community, that, for instance, the black histogram here shows that the helium core mass for single stars. We already know that from single stars you end up producing two massive cores to be explained from observations. So if you count up the ejecta and you assume something about the neutron star remaining, and then you get something observationally, the stars from the single stars using wind prescription at solar metallicity are just too massive. So that's the whole reason, like, people have been actually talking, not the whole reason, one of the big reasons people have been asking whether binaries can do the job. Because you want to create type 2D supernovae that are that were initially less massive. So anyway, this is not very constraining, but I think this one is slightly more not constraining but indicative of whether we can believe our models or not. So for again, this is solar metallicity type models, this is low metallicity type models, and on top of here I have plotted, so what we're looking at is a histogram in the HR diagram space where progenitors are red and companions are blues, and correspondingly any constraint that we have from observations for the progenitor and the companion, this is pre-explosion, are shown in crosshairs. As I said that both solar metallicity and low metallicity kind of are in the ballpark of where the models are predicted, so there's no distinguishing part. But like I said, at solar metallicity, they have this huge population of binaries that survive because of weak winds. And they show up at a particular part of the HR diagram. That is, this is on the helium main sequence for the theorists in the audience. And the funny thing is that if you follow the red crosshairs, which is the indications from observations, and then you see that yes, you are able to be on top of the observations with the models here. There is this part which is extremely sort of compact progenitor systems that are not seen from observations. So of the 5 progenitors that we see, many of them are yellow and red supergiants, as most of you know, but we don't see any blue stuff. So the question is, if this group is needed to explain rates, then why don't we see them in observations? Is this a bias, or is this that the models are wrong? And so, like for instance, so you can think of this as a testable prediction for the model. So our model, if you want to be able to, if you want to have binaries explain type 2Ds, you need to allow for some group like this compact to remain behind. And if they remain, then the question is that eventually you should be able to see them in observations. That's sort of like the portion that's testable. Of more interest to you people, some of you people here, would be the circumstellar medium properties. So again, here the top panel is solar metallicity, the bottom panel is subsolar metallicity. As I said, these are the ones that explain the rates much better. So so here, observationally speaking, so observationally you get the circumstellar medium density, and here I'm plotting the wind mass loss rate the wind speed over the wind mass loss rate. This calculation is done with a lot of caveats, and we can discuss this later, but there's one key point to take away from this. So anyway, if you plot it like this, which is many times what observers will plot for you, And then you obviously get diagonal lines in this parameter space from observations, which is what this purple region is. And then you plot what you expect from the models as a probability density. Again, this group that shows up, that is there. So what are these? These are extremely compact progenitors. So they are blue in nature. And what we've assumed here is that the wind, the circumstellar medium was primarily shaped by the wind mass loss from the progenitor system. So since these are compact and we are assuming something about the wind speed that left the progenitor star, so for instance, we expect that the material was leaving the progenitor with the escape velocity of the progenitor star. You typically expect that you would have higher wind velocities. So anyway, it's set by some assumptions that we make regarding the material that was lost from the system. But what is key to keep in mind is the fact that these, again, as before, this group, it has lower densities than is predicted from observations. Now again, you can ask whether there is a bias that would prevent you from seeing this, and there is reason to think of. So there are two types of questions to ask. Can I solve this somehow at the end stage of evolution? So stellar eruptions. And if you're willing to take that into account, and Dan has expressed interest in taking some of the models and making them have some prescription in them that allows for eruptive mass loss to be considered. But if in the late stages you have eruptions, then you can probably push these models into the region where you observe, or you can think of them as an observation bias, because if these low density circumstellar medium would be also difficult observationally to observe. So the way to think about this is that if this group is needed to explain the rays, then you should also see them observationally. Since you don't see them observationally, the question to ask is the model correct, or is there a bias in observations, and we will eventually see them, and so that's the other testable aspect. And I just want to quickly highlight the fact that this kind of work, when we do sort of large-scale population synthesis scale calculations, are useful to eventually constrain individual progenitor properties and can aid in companion searches, for example. So this is the paper that we published in 2018 that was looking at 2016 GKG. And 2016 GKG at that time was the most recent type 2B with a detected progenitor. And we took this into a Bayesian calculation and eventually had a set of models, and we had predictables for a whole bunch of properties that were yet to be seen. So for instance, this was the HR diagram probability density from our models. So the black crosshair was the detected progenitor, the attributed progenitor that we saw. And everything else here, even though it's not very constraining, of course, they're all, the theorists will appreciate this, there's nothing very interesting happening. But these are all the companions, which, as with the color scale before, are in blue. This is the probability density of the expected companion. If you were interested in using HST and UV filters to go after some of this, and you need to motivate why you needed your particular filter set, a calculation like this would tell you that you expect something from the models indicate that this particular set of observations are implied from modeling, so can better motivate you to get the program better motivated. So with that, I'll move to my final slide, which is that. I started off and I said I wanted to ask what the progenitors of type 2B supernova are. Are they singles? Are they binaries? Because that's all I wanted. I didn't have rotation or stellar eruptions. But remember that I said I wanted to make sure that I explain all observations. Now, as you saw earlier, that particularly it's not that we disagree with observations. Most of our models are typically able to explain observations. But what was new in this work was we tried to do this statistically, which means we took into account probability densities based on the Berg properties and sort of populate the parameter space that way. And if you did that, you get a few things. First, your rates disagree for binary calculations at solar metallicity, given the fact that your winds are too strong. If you're able to modify the winds, as I mentioned, you do better. So that's number one. So you get, we think there should be weaker winds at solar metallicity as another line of evidence to the growing body of the weak wind argument. And that you have, so this one actually I didn't go over, so let's skip that. But then the last thing is that eventually you want to be able to have some testable predictions. So there are, even though we're not distinguishing in the set of observable properties that our models are indicating, there are groups and clusters that show up that are implied if you really want to explain the type 2b supernova rate population. For instance, you expect to have very compact group progenitors expected, regardless of metallicity, and that's because ask me later if you're interested. And then if you're willing to do calculations like this, so this is for type 2b's only. But if you're willing to do calculations like this more extensively, it can help you then get back at explaining the progenitor population. So if you given a progenitor that you see and its properties, you can then end up getting a progenitor distribution that is rather than getting one or few channels that explain it, you get progenitor distributions, property distributions from the models.
Questions for Ari?
So aren't solar winds not actually very well understood? I mean, couldn't you have very different solar winds for essentially similar stars that have maybe slightly different rotation parameters and magnetic fields?
Yes.
Yes, so.
I'm not sure how, I'll try to answer your question, and if I don't at the end, just let me know. So solar metallicity winds, so for instance, let me go back here, the one that I'm showing. Solar metallicity winds, yes, they will be modified because of rotation, any additional physics in the models that will drive, that will change how the wind is being lost from the system. This is non-rotating, but even these, for instance, are expected to be overestimated in order of going backwards. So for instance, this is main sequence winds, these are dust-driven giant winds, and these are Wolf Rayet stage winds. And if you, based on my knowledge of what is being said, is that these are the ones that are most uncertain, followed by this, and these are the best understood. So, does that answer your question?
Yes.
Okay.
We don't really know.
Or you ask me later. Yes. It's not if we do. It's not if we don't really know anything. I mean, we've got to work with what we have.
Questions? I have one. So when you're comparing your supernova rates to observations, and you have the constraints for the solar versus subsolar, how is the metallicity determined observation? Is it based on like H2 regions in the galaxy?
So for these, so you mean the observational?
Yeah.
Okay,
yeah.
I'm going to speak for Maria Mojas because she corrected me on this. So apparently they okay, I could be wrong, I'm going to try. They look at, so they have, galaxies for which they have sort of like some colors that they get for the host galaxy. And they use cuts on the galaxy colors as a proxy for the galaxy mass. And then, so these are not function of metallicity, they're a function of mass of the galaxy. And then you have, so this corresponds to a mass cut in the galaxy, and I just chose a mass cut that was between LMC and SMC because this metallicity was represented between. So I chose a mass. So if you look at their distribution, there's a mass cut for the progenitor for the host galaxy, and I just chose the one that was representative to put these numbers here.
Okay.
Yeah.
All right. If there's no more questions, let's thank Ari again.
Thank you.
So we completely changed gears right now, and we have a full room today. It's nice to see all these solar faces around. With us today we have Dr. Tim Bastian, who is coming all the way from Charlottesville, Virginia. Tim has a bachelor's in mathematics from the University of Chicago. Then he did his PhD in astrophysics from the University of Colorado. Shortly after that, he became a Jansky Fellow at the NRAO, and if I'm not mistaken, never left. Then he stayed there as an astronomer. Afterwards, Tim became an assistant director of the NRAO Office of Science and Academic Affairs in 2009, and then he developed the Department of Science Support and Research, for which he was the Assistant Director until 2017. And then he decided to step down to do some more hands-on science. He's leading ALMA and JVLA. And his main interests are relevant to radio emission from the sun, but occasionally he's also interested in stellar and planetary radio physics and exoplanets. Today he will talk to us about radio propagation diagnostics in the inner heliosphere in the era of Parker Solar Probe Plus, and that's why we have all the solar people around today. And he will be around for today and tomorrow, the full day, and you can sign up for his schedule if you want to have a meeting with him afterwards. So we don't.
Okay. Thanks, Sophia. Just one small correction. I don't lead the ALMA and VLA. I am leading the solar commissioning effort for ALMA and VLA. In fact, we had a very painful telecom this morning. So as Sophia said, I'll take things a little bit closer to home, just a few microparsecs away. This is not an ordinary star. It does not have a very robust wind, as you know. It's only a few times 10⁻14 solar masses per year, but nevertheless it does have its interest. My own interest in the solar wind dates back a long time ago, actually to the mid-1990s, when I wondered what the limitations were by turbulence in the sun's corona, how it limited seeing at radio wavelengths. And that sort of drew me into the more general problem of propagation phenomena in the solar wind. So I'm returning to this interest, of course, in large part due to the launch of Parker Solar Probe. So I'm sure that most of the people in this room have heard of Parker Solar Probe, but for a few of you that have not, it's an audacious mission that was launched just last August. It is going to be eventually dropping in all the way to within 10 solar radii of the photosphere. Really quite remarkable. And just to put that in perspective, the Helios missions of many years ago only got into about 0.3 AU or 65 solar radii. Already, with the November flyby, the first perihelion passage, PSP came into 35 solar radii. It will be executing about 3 perihelion passages annually, using Venus gravity assist to shed angular momentum and get ever closer to the sun, with closest approach happening in 2024. So there'll be many opportunities to co-observe with Parker. Up here are sort of the primary science objectives, very broad in their scope. But basically, this offers an unprecedented opportunity to characterize solar wind turbulence, and this is the one mention of high energy phenomenon for this group, solar energetic particles near their origin. So there's a lot of interest in providing comprehensive and complementary observations of the sun and the corona. These are needed to provide global perspective and a broader framework within which to interpret PSP data. Ground-based radio observations are certainly part of this effort, using a variety of direct and indirect observations. In the case of this last science bullet, direct observations are rather more productive. Radio is a very vast range of wavelengths, 7 orders of magnitude or so, ranging from 7 millimeter with ALMA, and it's a bit like peeling layers of the onion. Down in the chromosphere, thermal free provides the capacity. So ALMA is an excellent instrument for probing the solar chromosphere. As we move to longer wavelengths, lower frequencies, the JASCI Very Large Array and some solar dedicated instruments begin to probe the upper chromosphere to low corona. Thermal free, thermal gyro resonance, and non-thermal gyro synchrotron come into the fore. Yet longer wavelengths, coherent emission mechanisms begin to play a role. As we go to the low frequency instruments, coherent mechanisms and non-thermal gyro synchrotron dominate the emission typically. There's been a lot of activity over the past decade in the development of low frequency instrumentation. A lot of this is driven by cosmology, efficacy ionization, and so on. It has particular interest in the sun, although people are, of course, piggybacking on these instruments to do solar work. And then out in space above the ionospheric cutoff at hectometer, kilometer wavelengths, spacecraft like WIND, Stereo, now Parker are carrying spectrometers to do spectroscopy of coherent bursts. And we hope we're in extended phase A that Sunrise, a flotilla of 6 spacecraft, will be able to do interferometry of radio bursts from out in space. But for the second science objective, determine structure and dynamics of the plasma and magnetic fields of the sources of the solar wind, this is where indirect radio means can play a significant role, I think. The Fields experiment with P.I. Stewart Vail is making in situ measurements of particles, of electric and magnetic fields, doing radio spectroscopy, measuring dust parameters, and the SWEEP package is making direct measurements, of course, of electrons, protons, and alphas. Justin Casper, PI, formerly of Harvard, now at University of Michigan. And I'm looking forward to talking to some of the members of the SWEEP team who are here. So, solar wind spectrum. The sun is an ordinary star, but it offers an amazing laboratory to look at MHD turbulence, the generation of such turbulence, the evolution of such turbulence, and the way it mediates or modulates other phenomena, which I'll get to in a moment. I mean, I think we're all sort of used to thinking in terms of Kolmogorov-like spectrum, power spectrum of turbulence. This is frequency here measured in situ by the wind experiment with a fast solar wind stream. And it has all the characteristics of a Kolmogorov spectrum, sort of an input scale, an inertial range with depth minus 5/3, and a so-called inner scale followed by a dissipation range. Now, things are a bit more complicated using density diagnostics, as determined by density fluctuations. I show up here a structure function, which I'll get to in a few minutes. You can sort of think of it as if we flip it around the vertical axis, it looks kind of like a power spectrum. Up here, Kolmogorov-like, but then something odd happens at intermediate scales to small scales. The spectrum flattens. In other words, there's excess power above Kolmogorov in density fluctuations. Now, there's a lot of activity on the theoretical side about what this means, in fact. One of the prevailing ideas is that oblique Alfvén waves, kinetic Alfvén waves, begin to play an important role as we get to small scales approaching the ion inertial length. And that far from being a passive scalar, sort of along for the ride, density fluctuations become an active player, leading to enhanced density fluctuations and ultimately dissipation through Landau damping or resonant interactions with ions at the ion cyclotron frequency. So some subsidiary questions to that central broad science theme of Parker relate to turbulence. How does MHD turbulence develop and evolve in the solar wind? What are the dissipation mechanisms? What role does it play in mediating energy deposition, meaning heat, in the solar wind? How does it modulate the transport of energetic particles in the solar wind? Both those produced by the sun itself, solar cosmic rays, and those external energetic particles penetrating into the atmosphere. These are not new questions, but these are new mechanisms for gaining some insight. So remote sensing at radio wavelengths. This is just some of the phenomena that we can observe. This is by no means an exhaustive list, but these are sort of the observations or the technique that one can exploit, and this is the plasma property that one can infer with an appropriately designed experiment. So for example, I'll be talking primarily about angular broadening, since in some ways it's the simplest to understand. Spectral broadening is very closely related. If I have time, I may mention something about intensity simulations. Probably most of you have heard about doing spectroscopy of scintillation spectra using, say, a single dish in the weak scattering regime. But there's some interesting properties of scintillations in the strong scattering regime as well that we may be able to exploit. Then, of course, we shouldn't forget Faraday rotation as a tool for probing the magnetic field along the line of sight to the sun's corona and solar wind. So let me just mention a couple of preliminaries, freshman physics. Fully ionized plasma, the refractive index, is given by this simple term, 1 minus plasma frequency squared over the observing frequency squared. And if this observing frequency is shown as let's say angular frequency rather than a cyclic frequency, given here, if it's much larger than the plasma frequency, then we can expand the refractive index in this way if we take the density to be a mean plus a fluctuating part. And so we see that the fluctuations in electron number density lead to fluctuations in the refractive index, which, as you might imagine, will have an impact on the radiation incident on such fluctuations. If we have radiation incident on a uniform slab of plasma, thickness delta Z, then the incident waves undergo a phase shift, which is, again, just proportional to the fluctuation of density. Okay? So that's for a slab. If we have a density wedge, like so, a density gradient, that yields a phase gradient. And to the extent that the direction of the incident radiation is given by the phase normal, this is just refraction. Okay? Simple. If we have an inhomogeneity with a transfer scale D, well then diffraction comes into play. The radiation is forward scattered into a cone with a characteristic angular width of lambda by D. So these are all very simple ideas, but they conspire in various ways to give you leverage on the medium with these inhomogeneities present. So angular broadening. Here's a schematic, a distant point source. Let's say a quasar that is point-like, unresolved, spatially coherent. Plane waves incident on the foreground solar wind, which is blowing away from the sun with some characteristic speed, a few hundred kilometers a second. Sort of in a thin screen approximation, and we sort of treat this delta Z, which is small compared to 1 AU, non-absorbing phase-changing screen. What emerges is this corrugated wavefront. Each of these little sections of the corrugated wavefront has an associated wave normal, and you can see right away, intuitively, that your point source is no longer point-like. It's been spread into an angular spectrum. So it's been blurred out by this medium. So angular spectrum with a characteristic width 1 over wave number times coherence scale. So I'll be talking a little bit more about structure functions. I introduce it here as simply the phase difference between the line of sight phase delay between two sensors separated by some baseline S. Okay? So square it, take the expectation. It is, by the way, related to the 2-point correlation functions at S equals 0 and S in this way. So you can describe the fluctuations in the medium either through a 2-point correlation function or this structure function statistic, which has a pleasing property. The spatial coherence of the electric field is related to the structure function through this very simple expression, that the electric field covariance is just the structure function over 2 exponential. I'll come back to that. So coherence scale is simply the transfer scale in which the structure function assumes a value of 1 radian squared, so that's the characteristic scale. As I mentioned, the angular width of the source is 1 over kr sub 0. As soon as you spread out the source on the sky, you can also sort of intuit that there's going to be temporal broadening, because now you have radiation coming from different directions and traveling different distances. And because it's sampling different bits of the solar wind, there is a projection either towards or away from you, which is going to lead to spectral broadening as well. So you can exploit all of these to learn something about the scattering medium. Intensity simulations, I don't think I'm going to talk about this right now. I'm going to defer to the end of the talk if there's time. But the strong scattering regime is an interesting one. Rather than so-called diffractive simulation, which is on a very fast time scale, there's so-called refractive simulation, which occurs on large scales at a much more leisurely rate. So the example I wanted to pursue a little bit today is angular broadening. As I mentioned, the phase structure function is given by this expression. It's related to the spatial spectrum of electron density fluctuations through this integral expression here for isotropic homogeneous turbulence. And if we were to, say, characterize the spatial spectrum by power law with, say, an inner scale, given by this expression, then you can solve this integral. The result is somewhat unpleasant. It's a confluent hydrogeometric function, but it does have pleasing asymptotic properties that converges to fairly rapidly. Namely, if you're sampling scales greater than the inner scale, structure function depends on S, just as this simple exponent alpha, which is related to the spatial spectrum of electron density fluctuations. And if your spatial scales are less than the inner scale, then it just simply goes as S squared. Okay. And this is for so-called shallow spectra, where 0 less than alpha less than 2. Great. All right, do that. So what's the point of all this apparatus? Well, the thing is that radio interferometers like the VLA are basically machines for measuring the structure functions. Okay? They're a Fourier synthesis telescope. In other words, the VLA simply measures the Fourier transform of the sky. Suppose you're looking at a point source. Well, the Fourier transform of a point source is just, a delta function, which is a DC offset phase 0. So very pleasing properties, point function. But if you have an intervening turbulent medium, we saw that the electric field covariance, we're essentially measuring the electric field covariance, is degraded by loss of coherence in the phase. So I had this expression earlier, structure function here, related to electric field covariance here. You can see that if this is the visibility we measure, inverse Fourier transform of this exponential leads to something which is Gaussian-like in the image plane. That's certainly true if we're looking at baselines less than the inner scale, where we have an S squared dependence, and we have an e to the minus S squared here, and that's just a Gaussian. But because it's an e to the minus alpha, and alpha less than 2, it looks sort of more like a Lorentzian profile in the image, again, if you take a cut across the source. Be that as it may, it can be used as a productive probe solar wind. So I was going to run through some observations from a pilot program a few of us did, and Adam Dabelski, who was postdocing with us at the time, and Angelos Relitas, who some of you I'm sure know quite well, to shake out the Jansky Very Large Array for this kind of work. The big JVLA is no longer the old classic VLA. It's been broad-banded. It's much more sensitive. So one of the nice attributes now is that we have many, many more background sources that are accessible to view through the sun, solar, and the corona. In past proof of concept experiments were done, we learned a certain amount, but we typically relied on sources of order of Jansky or so in spring. And those are few and far between, so they can only be used occasionally. But now, in fact, we selected program sources that are of order of Q10s of millijanskys, of which there are many in the sky. We happen to select those from the JBAS survey, compact view of calibrated sources, flat spectrum sources. So they're being used partly to test and partly to sort of revisit some of the old problems that were uncovered during the 80s and 90s, but to validate wideband observing, search for spectral breaks, basically verify previous observations, explore the feasibility of using refractive simulations to further constrain the spectrum. So this is very much a hunting expedition, and I'll mention at the end a much more systematic program that we've undertaken for Perihelion passage number 3, which is just last month. VLA we use in its A configuration. It's the most extended configuration. So the largest baselines, or scale S, is about 36 kilometers. Angular resolution there is about 1.5 arc seconds at 100 gigahertz. So divide by gigahertz and get the angular resolution. We use frequency bands of 1 to 18 gigahertz. Why use different frequencies? Well, you may have noticed it went quite quickly. The structure function depends rigorously on wavelength square. So as you get close to the sun, the structure function amplitude goes way up very fast, like R square, or sorry, density squared. So like R to the 4. And so to sort of click back down into a reasonable range, we go to higher and higher frequencies to approach the sun and keep it in band. And you can also see from the instantaneous coverage in S that we have very pleasant coverage. In other words, we have lots and lots of measurements in S at many different position levels. So we have good coverage of the structure function. The target sources, we just looked at a handful. In fact, a total of 11 sources in 24 sessions, 15 of which I showed here. Some were over-resolved, some were under-resolved, some had technical difficulties, meaning wrong quantizer gain set, and so they were discarded. Typical observation entailed about 15 minutes on the source, which is long enough to be in the so-called ensemble average regime to get you a good measurement of the structure function. As I mentioned, we exploited the lambda square dependence of DS to perform measurements near the sun, and you can see that we sort of get just inside 2 solar radii out to about 7 solar radii for this pilot. So what do the data look like? Well, this is an example of the data, calibrated data, but otherwise nothing done with them. What we see here is this is now essentially the scale S in units of wavelength. So we see that we go out to about 1 million wavelengths, so 0.2 of an arc second resolution roughly. And it looks kind of messy. It doesn't look very clean. It doesn't look Gaussian-like or even Lorentzian-like. But if we do the inverse Fourier transform, it does make a nice image. It's scatter broadened, blurry. It's right away, you're struck by the fact that it's anisotropic, because the turbulence itself is anisotropic. However, if we fit in the visibility domain to this expression here, so here's the structure function and here's the refractive offset, because we do have a general gradient in the coronal density that yields a small refractive offset that we need to correct for, and rectify the data with a model. Now plot the visibility amplitudes normalized to the measured flux, and this is in units of coherence scale. Right, so well, we'll show that over here. The data resolve themselves in this very nice pattern. Okay, so that seems to work pretty well. And then, because of the simple relationship between structure function and the measured visibility, we can compute the structure function as just -2 log normalized visibility and opposite structure function. And so here it is on log, and this is sort of nice power law, 1, 1. So this is 1 radian squared in the structure function at the coherence scale. So we can sort of extract alpha, the degree of anisotropy, from these sources. And here's sort of a confusogram showing what that looks like. And I apologize for the mess. The green ball here represents alpha equal 5/3 fiducial, so Kolmogorov-like spectrum. And this circle here represents a fiducial of 10 arc seconds for the source, rescaled to the 20 centimeter wavelength. So this is what the source would look like on the sky at a wavelength of 20 centimeters, with this being the fiducial. And you can see that all of the sources are highly anisotropic. They have axial ratios of order 5 to 10. And you'll see that if we now plot the lollipop stick in blue perpendicular to the scattering, it aligns with the coronal magnetic field. In other words, the turbulent eddies are drawn out along the sun's coronal magnetic field. Scattering is preferential perpendicular to the small scale. And so you can use the perpendicular to the scattering in turn as a proxy for the orientation of the coronal magnetic field. So we have, you'll also notice that most of the circles here are smaller than that. In other words, as I started out, I think in the third slide, the spectrum as inferred from density fluctuation measurements indicates that at small and intermediate scales, we flatten from Pomodoro to excess power and fluctuating density at these intermediate and small scales. That's certainly borne out in the inner corona here, although there are some notable exceptions. There has been a bit of an issue, I would say, in interpretation of the various kinds of propagation experiments that one can employ. And the one I want to highlight briefly here is between using IPS spectroscopy on the one hand and angular broadening measurements on the other. I would say that previous generations of observations, and this is just one example of such a paper by Ramayan and all back in 1994, did not really find any compelling evidence for dissipation scale at all, using the kinds of techniques I just described. But on the other hand, IPS, interpreting the roll-off here at the high-frequency end and big, does routinely interpret this roll-off in terms of dissipation scale, and it seems to scale at least beyond 10 solar radii, more or less linearly, where the inner scale basically being the elongation from the sun, so 10 kilometers for elongation of 10 solar radii. Some more recent measurements by Yamaguchi in 1998 seem to indicate a steepening here. So, you know, what's going on? The VLA is ideally suited to measure dissipation scales. It samples from, you know, a few hundred meters all the way out to tens of kilometers. It's right in the sweet spot. So is there a fundamental inconsistency here? Well, maybe. For the pilot data, at least two lines of sight yield spectra that are steeper, or somewhat steeper than Pomodoro. These two lines of sight. Somewhat bigger signals. And one source yielded a broken power law, not a simple power law. Are those reasonable? Could they be interpreted in terms of inner scales? Well, maybe. Here's the red points up here with the noise. These are the measurements. You can see the break here a little bit larger than the coherence scale. It certainly doesn't break to a slope of 2 that you would expect when the baseline is less than the inner scale. It is certainly a discrete break, though. If we interpret this as a dissipation scale, if it's a marker of a dissipation scale and plot it, well, it's sort of bang on from the IPS observations. And these two we should take as upper limits. In other words, we see no sign as a break, we simply see the steep spectrum. And if we take the upper limit as where we disappear into the noise, it has to be at least 3 kilometers at the particular elongations, which again is okay, maybe. But the question is then, why don't the other lines of sight show any evidence for this sort of spectrum? And why don't we see a discrete break to a slope of an index of 2? And I can make some arguments and we can talk about it. In fact, I'm hungry for feedback from many of you who have a background in turbulence and particularly solar wind turbulence. Now, I wanted to end by saying a few words about perihelion free. As I mentioned, that took place just a bit more than a month ago, back in September 1. We observed for 2 weeks on either side of the perihelion, so mid-August to mid-September, and we plan on doing so for future perihelion whenever the VLA is in the A configuration, which is every 16 months, as we'll show. It's a trimester scale. There's the, I don't know if you can see that very well, but it actually happens with remarkable speed. And what's nice this time around, I didn't really dwell on this when I went through pilot observations very quickly, but those were performed in 2015 over the course of 4 Carrington solar rotations. And the sun was actively sort of declining towards minimum warm end levels, but it still had, it had no well-developed polar coronal holes yet. It was by no means a minimum corona. It had active regions present, slow and fast solar wind, and so on. So interpreting this ensemble of pilot observations in any coherent fashion was unwise at best. But what's nice about this latest campaign is that the sun is essentially at minimum now. Very simple corona, nice polar coronal holes, and we expanded our coverage to include all of these lines of sight. So We have a dense grid of background sources with which to probe this minimal corona. So stay tuned. As I said, this is very much work in progress. We're also thinking of designing experiments going forward to exploit some of the other phenomena that I mentioned. But let me just conclude with some remarks here. The pilot program did validate past results using the VLA. It did show that we could use quite weak sources, and therefore we can do this sort of turbulence homogeny using dense grid background sources. So in support of, for example, Parker. In contrast to previous work, we may see hints of an inner scale, but there still is this puzzling disconnect between the IPS results and what we see. It's really only 20% of our pilot sources that we see this. Going forward, we very much need to do joint angle broadening IPS observations at the same source at the same time to try to understand this discrepancy. Also of great interest is going to get lower frequencies and longer elongations outside of the so-called Alfvén zone or Alfvén radius. Faraday rotation measurements of millisecond pulse cycles is something we want to pursue. Pursuing both angular broadening and Faraday rotation measurements of trenches, see a loop going off the sun as it goes back to active phase. And then finally, we'd like to push into very long baselines to begin sort of studying this transition from flattening here to the more chromogora-like development of the spectrum here, and understanding how it evolves both with radius and with position angle and the solar cycle. So it's a big group. Okay, but I'm going to stop there and we'll talk about simulations if anybody wants. Thanks.
Yes, Ed.
So just a fundamental confusion. You seem to imply that the dominant source of the signal is from where the line of sight is closest to the sun.
Correct.
But the contributions along the rest of the line of sight are managed, are small, are
well, yeah,
consistent.
this is something. Yes, the thin screen approximation is valid, but we still have a line of sight integration through different media. And basically, more than half the contribution comes from an angular width of 60 degrees, or a radian. And you might well imagine that if you map out 60 degrees from the surface of the sun, you actually are crossing many structures, right? And so an overdense structure could have an effect, an underdense structure could have an effect. And so I mentioned that we don't see a nice clean break to an alpha of 2 when we're below the inner scale. Instead, it's much softer than that, flatter than that. That softening may come, in fact, from this line of sight integration.
So have you done forward models where you just take, pretend that I know what the solar wind looks like and see what the signals
that actually has been pursued at length and in detail by Faraday rotation measurements. It has not been looked at in detail for these sort of angular broadening measurements, but I think that is something that should be done. Yes.
But that would confuse your spectral break measurement. It wouldn't necessarily confuse the actual power law, the spectral index of the turbulence.
Well, if you add power laws at different slopes, you're always going to get something concave up, right? And we got something broken down. Now, you could argue that the lower part does show a little bit of concavity if you look at it. It was a pretty clean break, meaning if you had lots of different structures with different resonant frequencies because they have different magnetic fields, you would think that would greatly soften that break frequency.
I'm asking about the measurement of the actual spectral index, though, in the inertial range. If you add a whole bunch of power laws that have the same spectral index, you get a power law with that spectral index, right?
True.
So, am I understanding correctly then that there's no line of sight effect associated?
Well, for the most part, for 12 of those 15 sources, it was a nice clean power law with no sign of convexity or concavity. Mm-hmm. So it suggests that that it's dominated by very similar plasma along the line of sight. They may have different amplitudes, but the slope does not change.
Well, or different field angles, right? Like you showed it's very anisotropic.
Well, it's anisotropic in terms of its behavior perpendicular to and parallel to the magnetic field.
Right.
Right. And it's also true that you might expect something closer to infinite axial ratio, very, very large axial ratios, y 5 to 10. Well, you have slight changes of the magnetic field along that line of sight again. It's probably going to weight that down.
Is it slight or is it actually a lot?
Well, again, this is where the suggestion of EDS comes into play. It really does need to be modeled in detail. So it's going to be sort of, the O minus C kind of idea of sort of playing this computed model.
One more question. Yes.
Some time ago, Steve Spangler tried looking at extended polarized sources, to look for fluctuations in the magnetic inertia. Are you going to try something like that?
Yes, I talked to Steve Cranmer about that, and Jason Cooey, who's Steve's former student, who's NRL. He's visiting, in fact, next month to talk about the next round of proposals. Not going after extended polarized sources, that is a very difficult game to play, but going after millisecond pulsars instead, where it puts you up ahead because you can measure not only Faraday rotation, but dispersion measure as well, and get the grip on the line of sight density.
Quick question. To what extent can you localize CMEs well off the sun? I'm asking because we here at Harvard, together with MIT, have an X-ray spectrometer on the OSIRIS-REx mission, which is at roughly 1 AU, but cranked around the other side of the solar system right now. And in February, we saw an increase in background count rates that we think are particle-induced events that rose and fell on a roughly 1 week time scale, and is most naturally explained by a CME in that region. So can you, what's the time coverage that you have in this whole mapping exercise?
Well,
is it possible there's
for the latest experiment providing support for the third perihelion passage, we observed really a handful of targets a day for an hour or so. So the coverage is not terrific in terms of hunting for CMEs. It's purely serendipitous if one happened to cross the huge range of. So I would say that propagation observations of this type are probably not the most efficient way to look for CMEs. I mean, there's the white light chromographs on stereo, SOHO, the whisper instrument on PSP itself, which will be looking at CMEs.
But over a broad field of view?
That's an extremely broad field.
Okay. Good.
But I would say talk to Russ Howard or Angela Solis.
So how do you choose your sources? It wasn't very clear to me. You saw them.
Oh, the sources we chose, basically they're occulted by, or nearly occulted by the sun. I have a big catalog of sources. Everything that is compact, flat spectrum, greater than 50 millijansky in the northern sky is JGAS catalog, plus the VLA catalog of calibrators of A configuration, which are point-like. And so you just push them through and compare with the solar fungus, so you can determine when to observe them because they're a particular elongation of position.
Any final questions with me? If not, let's thank you. Can we give it in the you can sign out
So their configuration are just kind of predefined when they're in the different modes. Is that
Well, they sort of this is the reason they're part of it, but they also want to rotate through so that you get
Question I wanted to ask. So I checked these schedules before coming here.
No one was after me. Yeah. So I don't know if we want to have like a meeting.
It's also balanced between because you've got questions.
So there's nobody after. Like we want to have a group meeting.
Where are we going to meet?
Everybody has put their offices, schedule.
Just let me know.
Bastian, this is Jeremy Drake.
Hi, Jeremy.
Nice to meet you.
I know you by name?
Bad, I'm sure.
Yes, I'm afraid so.
That's a lot of questions, right?
Hi, nice to meet you.
So, well, the real question is about
And we're going to have to run among them.
Can I dump this stuff in the office?
I think it depends on what you're trying to model, right? I mean, if you're trying to model the propagation, I think that's right, yeah.
All right.
You start with just comparing
Did you want to get some lunch? Did you get
Did you have enough?
Yeah, the corona.
Yeah.
That's what I'm talking about.
That's right.
And so the core of it.
Okay, so I'll keep an eye on the email just to see if
We can also take
application to be sold. That's why I picked on you.
No, sure. And I think that what you're pointing out is, well, it seems to me like the energy budget is fine, so what's the problem, right? I know that there's enough energy coming in, and I know that I get more energy out than I put in, so why is this a problem, right?
Yeah, that's
And I don't think that is a problem. So from the question of solar heating isn't a where's the energy comes from question. I don't think.
I always hear it portrayed that way.
Well, okay,
I don't
it's-
go to
it's-
solar meetings because they're more specific in their questions. I go to people that are talking about supernova 1A progenitors and stuff.
Yeah.
And how they introduce their supernova.
Yeah.
And all of these questions have to come up there eventually. Let's start with the sun where we have direct information.
I think it's a much more mature question than that, which is like a really nice way of saying I think it's much more about minutia. Because the energy budget I don't think is in question. The question is what the modes are of transport that are dominating, right?
I'm starting to like the answer in the direction you're going.
Well, this is what gives everybody license, when they do some sort of an interesting model of transport, and then they find out that you could get enough energy out of this kind of wave if this kind of wave was being absorbed in this way. I've solved coronal heating, and that's why coronal heating has been solved 30 times over.
That's correct.
It's
like I'm acting as editor in chief of doing an issue on consciousness.
Yeah.
I will get 30 manuscripts that all have a theory of consciousness rising in that little brain structure that's 1/2 centimeter to the left and 2 inches above. And blah, blah, blah. It's just that every author has a different source of where consciousness is. It's in the Omegatum.
Well, and you're way more in the weeds than this. Well, I'm not sure about that.
Yeah, you're right. So I'm asking kind of a similar question here. We're a little saturated with pictures of the heating of the solar corona, but nobody's been making it kind of an intuitive.
I think maybe we could draw a tree, and I think that like the bottom branch would be the AC/DC question, which is whether you have continuous wave input from granular motion, right? The base shaking the bottoms of field lines, which is just the top end of what you're talking about with convection. And then having a totally self-consistent, turbulent cascade down to small scales where it gets absorbed into the plasma. Versus that's the DC traditionally idea. Versus the AC idea, which is where whenever you have criticalities that are introduced in the plasma, wherever you have magnetic reconnection and topological reconfigurations, you have explosive heating events. And which one of those is the dominant source? Because those are both happening, right?
But I was hoping that the solar Parker Explorer would, by the way, Gene Parker was my instructor or teacher.
Really?
Do you need this other stuff as well, just to
Taught
keep
the
it straight, or?
Thermodynamics course, and nobody in the class held these.
just this.
You had to
He's
know
not
more, you had to be
smart.
smarter than he was to get an A. And by his definition of smarter, I'm not sure how that worked. He was a very sharp guy.
That's a toughie.
He was a guy, you know, that of all the people as a university sharp.
Yeah.
Yeah.
He was
I'm also kind of got baby brain right
had all
now.
ours.
She doesn't say
That's
that.
I'm sorry, it's a distraction.
That's a hell of a superlative.
Yeah.
It's an
But
exciting
This was in
anyway,
Chicago, the old firm.
yeah.
In other words,
but mostly
was
stays
80 years old, so I was there in the 1960s,
short fiction.
the late 50s, early 60s. And so it was still the English for families.
We've got to figure out a way to get him here actually, because he's given some lectures at the birth of solar probe. It would be really quite a thing. But anyway, okay, so there's this ACDC thing, and different people have attempted to show, well, from the flares and from statistics of flares, and then from statistics of flares, they go to smaller and smaller scales, and we extrapolate to nanoflares, which is Parker's actually idea, right? To nanoflares and smaller reconnective events that cause explosive exchanges of energy that do the majority of the heating, right? So that's like one idea. And it's been pretty convincingly argued that you could get enough energy out just from that. And then another idea is on the DC side, so on the just ongoing cascade of energy. Well, you go through a part of the turbulence spectrum which Tim was showing here, where everything is alphanic and there's no dissipation yet. And we understand how that works pretty well, and it's pretty well observed. But then once it gets to the dissipative regime, it's nowhere near as well measured, and you're talking about nonlinear physics, and so there are
the turbulence is the last problem solved.
well, yeah. So there's no consensus about where the energy goes in the end, or I guess it all goes to heat in the end, but how it gets there.
Okay, I like that. I like the correction you made. Yeah, you've got the energy budget. That's a major problem.
Yeah.
But then how do you connect the dots?
Yeah.
But the relatively uniform curve.
And there are all these clues in terms of how the energy is partitioned,
Yeah.
and in terms of which species gets heated relative to which, and which species gets accelerated or is along for the ride.
And so I'm
There's
here
a lot of-
because it sounded from his abstract that he was going to show the movie that was going to answer that very question. Isn't that that's what the Parker probe is supposed to do?
Yeah, that's what it's supposed to do. It's
And
supposed
so
to go
he
there.
showed us this picture of the rotating sun.
It's going to get closer and closer, but it hasn't actually crossed into the,
that's what I'm trying.
not the closed corona, but it hasn't crossed the alphane point into the region where the heating is
It is
actively done.
coherent with the motions that it can observe.
Yeah.
I presume.
Well, it's true. What was I going to say? So, it's carrying plasma diagnostics, right, that can make the measurements on the right scales. It just needs to get there. And it's getting closer and closer to actually dipping in to the active heating regime, I guess is what you might
Would
say.
you like to hear some sort of decision? How it was written well, and I think I'm listening for in all of this discussion.
Sure.
So this would be turbulence theory as understood in the thermodynamics community. In other words, not turbulence done by astrophysicists. Everything that's done by astrophysicists has one fundamental flaw, which makes it 100% correct. And that is, every treatment is for linearization of all the equations, so that you have no dissipation. And because of the intensity, basically all of the simulations are useless.
Well, unless you see like perfect self-similar, spectra, right?
No, that's all parameters. I mean, all this CDM stuff. You've got like 50 parameters for LCD and theory. They like to talk about it. Oh, we have 6 basic parameters.
Oh, yeah.
You bump it up to 8 to give us inflation, and then...
I don't know how that interfaces with turbulence.
Okay, listen.
I have zero idea of how
Okay.
that kind of cosmology interfaces with turbulence. I don't know.
Here's how, here's the interface. The current picture that our and all simulations about is that there's no viscosity in the interstellar medium, and that you have this cold-dark matter stuff that dominates the mass of the universe, and it is viscosity free. And in that way, they build up this idea of building up the structure of the universe. The thermodynamics community starts exactly 180 degrees the opposite direction. The universe that's rotating continues. And then you remember the argument, the universe can't be rotating because if it were, there would be some radius for which that rotation would be utilized and would go home. What in fact happens is that turbulence in the earliest primordial stages of the universe will create all the structure that we see and fossilize. Are you familiar with this, how important fossilization is? Sure. Because that community, the thermodynamics community, considers all cosmic structure to have formed from the top down. That is, first the biggest voids fossilized, and then the clusters clump together on the largest scales, and then they need smaller clusters. And then other things happen, but the fossils of this early structure are what we see today. We see the voids, we see the cluster galaxies, and all that. So this is the crowd that I want to tell you should be listening to. And by the way, when the United States Navy has a problem with this intercontinental ballistic missile submarines, they don't go to astrophysicists. They talk to the turbulence community and ask them, how do we quiet down the subs? When I went to Ukraine, I saw a research group there that was tracking the American missile submarines by the tracks that they leave in the ocean. And maybe you are old enough to remember that we used to hear the Soviets launched from the Cosmodrome satellites, Cosmos 234, 235, and 236. Now, what were these 200 satellites doing? They were detecting American submarines at sea at operational depth. Because if you filter the photographs correctly, and these are just enough, photograph the ocean surface, and then in a magazine, I guess parachute, re-entry vehicle with parachute, pick up and go up into place. And I saw the optical bench in which they make Fourier spectra of the plates, put a filter in it, filter out all of the higher frequencies, and leave behind just the lowest frequencies. When you do that, you can see on these big plates, little faint trails, zigzagging, because they never quite straight line. These are the residual wakes of submerged American nuclear missile submarines at operational depth. Unfortunately, we were doing the same thing with the sonobuoy system. The Russians were getting the same information, but later on. I mean, it wasn't until a week later that they found out where our submarines were last week. And you see the problem, they got to get the spacecraft down, they got to do the analysis in the laboratory, they got to get a photograph.
But you got to tell me about the viscosity of the early universe.
Okay.
Because you left me there.
All right, so good. So the hydrodynamics community starts out a very different way. And they ask themselves, okay, you've got a universe that's overwhelmingly hydrogen. And so what do we know about hydrogen? Well, guess what? In the handbook of chemistry and physics, we can look up the one number we want to have, which is the hydrogen scattering radius. What's the radius of hydrogen atoms scattered? And from that, you compute what the mean free path of a ordinary proton or hydrogen atom
Right.
in the primordial universe was. And from the mean free path, you compute the viscosity, and from that, you get your cold blow-off number. So that's the way you compute when and where in the early history of the universe turbulence was an issue, what the cold blow-off number was. And they find that it wasn't until the universe had expanded very considerably, like to a redshift of about a million, that, I'm sorry, not to a redshift, I want to go the other way.
You want to go
So I want to go to like
Redshift
within
6.
5 minutes.
Z, you mean
Something like 5
you
minutes.
mean Z equals 6?
No, even higher. I want to go to Z equals 100,000.
Okay.
At that point, you're starting to see the structuring by turbulence. You're starting to see structure work its way down. You're seeing the growth of the largest structures, and those are the voids. Those became cosmic voids. And then after that, the superclusters of galaxies would have condensed out. And the thing about this is it's controlled by gravity, so that once you have a universe that's not quite homogeneous, but rather there's low density fluctuation here and over there, and then it notices its self-gravity and kind of compresses in, and then the linearization theory says, oh, at that point a pressure builds up, and it pushes it back out. Now, the hydrodynamics community says, oh no, wait a minute, you dissipated some energy in this process. So the pressure builds up, yes, but also it's dissipated some energy, so it can't push itself out as far as it was. And so now you're the first step in the hole on your energy budget.
Right. And
then it just keeps getting worse, and so gradually structure emerges because of dissipation of energy and because of this.
you're saying that's where the disconnect happens?
That's where the disconnect happens, and where all structure is formed, and everything we see today is fossils of these primordial turbulence events. And so what we consider to have been, go ahead.
I'm sorry, but I want to understand. So, but what you're saying is that the thing that's overlooked in the cosmology community then,
then ours right here, guys in picture,
is then everything that happens past that point. Everything that happens past that point where you have some sort of criticality that you got to
that is relevant. That Kolmogorov is relevant in the earliest moments of the universe.
Oh, interesting.
They think that, you see, they're starting with a universe of homogeneous gas populated by subhalos, whatever those are, and these quanta, these cold dark matter particles.
And then what is it that
whatever they are?
What is it that dictates the initial scale distribution of?
They put that in. The guys downstairs, put that in. That's the initial parameters. They put in a power spectrum of these initial parameters and say, now let's just let those go and dance and collide, and then they'll build up galaxies, and we'll show you how you do that. Well, all wrong. It's all made up. And notice that in the theory I was telling you about hydrodynamics community, there are no fitting parameters. Zero. Absolutely zero.
Right.
There's one number.
Right.
Scattering radius of the proton.
Okay.
You get the entire
Wait, do we?
Are you? Yeah. Am I breaking you guys up?
I have to join this too, actually.
Okay. Fair enough. I'll put it.
Sorry. What's your? We haven't met. Actually.
I'm really chilled, and I've been doing this stuff around here.
Nice to meet you formally. I've seen you around, but
yeah.
Mike
I like to go to things and see, keep these guys straight. Okay, take care, you guys. I'll see you around.
Have a good one. Go talk about solar probe.
Oh, the real hardware.
Yeah.
Wow.